Okay, so today we're going to be finishing this tutorial up. We will be doing the math contest questions, the remaining ones. So first of all, as a review, I'm pretty much just giving you guys the answer as to how to do the following math question that I'm going to show you guys. I want you guys to remember this rule right here. Number 4, so a to the x times a to the y is equal to a to the x plus y. Okay, this is the first one you're gonna have to use. And then next is gonna be this, the inverse properties of exponential functions. So you're gonna have to use the like the correlation between exponents and logarithmics. So remember that b is the base of the exponent, x is the exponent, and then c is the product. And the way you convert this into logarithmic form is you take b, which is the base of the exponent, and you place it as the base of the logarithmic. You take the product of the exponent, and then you place that in the brackets for the logarithmics, and then the exponent here, so x, you place it as the answer that you get for the logarithmic. Okay, so you're just going to be using these two things for the following math question. Hopefully you guys will still remember how to do it. Okay, so here, this question. The solution of the equation 7 to the power of x plus 7 is equal to 8 to the power of x can be expressed in the form x is equal to log base of b to the power of 7 to the power of 7. What is b? Okay, so please remember using the two things I just showed you just now. That will help you solve this question. Okay, so I'll give you guys 2 minutes to do this. Okay, time is up. All right, so check your answer. If you got C, then that is correct, 8/7. Okay, so as I said earlier, you're gonna have to use the product rule, right? So you have 7x plus, or 7 to the power of x plus 7 is equal to 8 to the power of x. Since you have the addition here, you can rewrite this as 7 to the power of x times 7 to the power of 7 is equal to 8 to the power of x. And then since you have one variable, right? You have this variable here, and you have a number here, and you have another variable here on the other side of the equal sign. So you want to move all of the terms with the variable, and you want to move it onto one side. So in this case, you can move 7 to the power of x onto the other side. So you get 7 to the power of 7 is equal to 8 to the power of x divided by 7 to the power of x. Okay, and then you can basically place the fraction in brackets, and you can move the exponent out, right? Remember like yesterday, I explained that you can uh, that these two are equal, right? These two are interchangeable. So the exponent applies to both the numerator and the denominator here. That's why you can write it like this. And then now we convert from exponential form to logarithmic form. Okay, so I just rewrote the equation here. Remember that it is in the form of b to the power of x is equal to c. And you can write this as log base b of c is equal to x. Right, so in this case, we want x on one side of the equation, right? So this 8 over 7 all to the power of x is going to be our b to the power of x here. And then 7 to the power of 7 is going to be the c in this case. So we place x here. We place the x as over here so that it's all alone on one side of the equation. And you have log, since this is the base of the exponent I want to figure out, right? So log of 8 over 7 of 7 to the power of 7, right? And we are asking for it in this form, right? That's why I wrote the x on this side. So if you look at the correlation, so let me write here, log b of 7 to the power of 7. You're trying to figure out b. This is b. So you have b is equal to 8 over 7, which is why it is option C. Are there any questions? Okay, then moving along. Now we can do this question. Okay, this question is kind of blurry, but it's still readable. So let d of n denote the number of positive integers. Oh, oops. Sorry, did not mean to do that. Let d of n denote the number of positive integers that divide n. Okay, let me write over it. So this is n, including 1 and n. For example, d of 1 is equal to 1. Since the factors of 1 is just 1 times 1, in total, this is just one number. D of 2 is equal to 2, right? 2 is equal to 1 times 2. That's two different numbers as its factors. So that's why it is equal to 2. And then D of 12 is equal to 6. So you have 1 times 12, right? You have 2 times 6, and you have 3 times 4. Right? In total, this is 6 different factors. So that's why D of 12 is equal to 6. And then this function is known as the divisor function. Let f, okay, the divisor function is talking about d of n. And then let f of n equal to d of n divided by the cube root of n. So let me rewrite this equation so that it looks clear. D of n is equal to the cube root of n. Cube root of n. Okay. And there is a unique positive integer capital N such that f of capital N is greater than f of n. For all positive integers where n is not equal to capital N, what is the sum of the digits of capital N? So for this question, just so you know, this question is a 12 AMC 12A problem 25 question. This is the last question of the math contest, so this is very hard. So I'm gonna let you guys use a calculator here. And you can only use a calculator here for this, for the cube root part of it. Okay. So uh yeah, that's the only thing you can use a calculator for. And okay, I'm gonna give you guys a helping tip. So a fast way to figure out what d of n is you take the exponents of the prime factorization and you add one to each of the exponents. So you have, I'm taking it from the question here, right? D of 12 is equal to 6. How can you get 6 very quickly? Is you have 12, right? 12 is equal to 2 squared times 3 to the power of 1, right? That's 4 times 3, that's 12. And you take the exponent here, so 2 and 1. You place them in brackets, so 2, this is 2 plus 1, times 1 plus 1. That is 3 times 2, that's 6. D of 12 is equal to 6, which is the same number that they got here. And this works regardless. So yes, that is basically a hint, right? You are trying to get the prime factors of n, and you want to find some sort of pattern in order to get the maximum n that you can get. Okay, so I'm gonna let you guys try this question out. I'll give you guys 3 minutes. So yeah, until 12:20. Okay, time is up. All right, so hold on. This seems to be slightly glitchy. Okay, there you go. Okay, so I already said this part. Okay, so to figure out n, we must find the maximum of the d of n over divided by the cube root of n for each prime factor, right? And the reason why you can do this is because let's just say, uh, so hopefully you guys remember the product rule for algebraic functions, exponential algebraic functions rules. So let's just say you have d of uh, 2 cubed times d of, let's just say 3 squared, right? These two are equal because you have like, so this is equal to d of 8 times d of 9. You can write it as this because of the because of this over here that I wrote about how you can quickly find d of n. So basically what this is equal to is 4, and then you have times, since this is 2, you add 1 to that, that's 3, and that is equal to 12. Um, and so this works simply because of that, because like you are just multiplying, you're multiplying the 2 cubed and 3 squared. You're trying to like, okay, so to you guys, this might look like this, right? D of 2 cubed plus 3 squared, right? That is how you write it as if you were following the product rule. But because we're not trying to actually find what 2 cubed times 3 squared is, we're just trying to find the number of factors. That is the reason why this works. And so that's basically the logic that we're following here. That is why I am writing each prime factor in itself. So I'm first starting off with 2 and then 3, and then you can go on to 5, 7, and so forth. So in order to find a pattern, right, you have to plug in the numbers. So d of 2 to the power of 1 divided by the cube root of 2. This is the part where I will let you guys use a calculator, because this is a math contest question. And so what they expect you to be able to do is remember all these cube roots, or they expect you to know some pattern or some equation that you can use to quickly find a cube root. But we, of course, do not know that, because that is a very advanced thing to know. So you can use a calculator here. That's what I meant. And this is approximately 1.59. And then going down, so we're just increasing the exponent by 1 each time. So this is 1, this is 2, this is 3, this is 4. And then, so for this one, that's d squared divided by the cube root of 4. That's approximately 1.89. And then over here, this is d of 2 cubed divided by the cube root of 8, which is equal to 2 exactly. And then d of 2 to the power 4 divided by the cube root of 16 is approximately 1.98. And as you can see here, 2 is greater than 1.98. And if you were to go further down, right, d of 2 to the power 5 divided by the cube root of 32, this would continue to go down. So this would equal to some number less than 1.98. And if you don't believe me, you can check. So this would just be 6 over the cube root of 32. Or I could check right now. Cube 2. And this would equal to 1.89. So as you can see, it just continues to decrease. And another way to think about this is that the d of n, so in this case, that's the d of 2 to the power of some number. This only increases by 1 each time, right? So d of 2n or 2, 1 here is equal to 2. Over here, it's 3, 4, this is 5, this is 6, and so on, right? It only increases by 1 each time. But the cube root, right? The number inside the cube root, this is 2, this is 4, this is 8. From 2 to 4, that's plus 2. From 4 to 8, that's plus 4. From 8 to 16, that's plus 8. So as you can see, it increases. So like the increase is double that from before, from the previous one, right? So from plus 2 to plus 4, that's times 2. From plus 4 to plus 8, that's times 2, right? And then so number inside the cube root increases much faster than d of n. And so with that, you can see that the pattern must mean, that means that the pattern must say that like it can only increase. So from here it increases, but then the second it starts decreasing, that means that from then on, this equation, the value that this gives will decrease from then on. Okay, so that means that this, I wrote too much, so I'm gonna erase this. Okay, so that means that we're gonna have to use 2 cubed as the prime factor for 2. Okay, so now moving on to the next prime factor, which would be 3, right? So we will be using like the same logic that we used here for 2. So this is 3d of 3 to the power of 1 divided by the cube root of 3 is approximately equal to 1.39. D of 3 squared divided by the cube root of 9 is approximately 1.44. And then the d of 3 cubed divided by the cube root of 27 is approximately 1.33. As you can see, it starts decreasing, right? So from 1.39, it increases to 1.44, and 1.44 decreases to 1.33. So that means that from then on, that means this value can only decrease. So we're going to use 3 squared. Now, what is 3 squared equal to? Well, 3 squared is equal to 9. And the division rule, right? The rule for if the number is divisible by 9 or not is that then the digits of the number must add up to a number divisible by 9. So the digits must add up to 9, 18, 27, and so forth, right? And if we go back, clear, and if we go back to the answer choices, right? The answer choices here, we have A is 5, B is 6, C is 7, D is 8, but E is 9. And 9 is the only number that is divisible by 9, and so therefore the answer must be E. And something that you could have done during the math contest was continuing, right? You could have continued the prime factors of 5 and then 7. And then after 7, the numbers would be too small. So they would basically be like they would be smaller than 1. Okay, so let's just say 7. Okay, so d of 7 to the power of 1 divided by the cube root of 7. So that is 2 divided by cube root of 7. And that is equal to 1.045. Right? That's approximately what it is equal to. This is still greater than 1. So this is fine. But then once we go to d of 11, right? D of 11 to the power of 1 divided by the cube root of 11. This is approximately or sorry, oops, 2 divided by the cube root of 11. That is 0.899. And as you can see, this is less than 1. And the reason why this that means that there is no prime factorization of 11. And the reason why is because if you look at d of 11 to the power of 0, right, divided by, and what is any number to the power of 0, that is just 1. So this would be the cube root of 1. And you add 1 to 0, so that's equal to 1 over 1, which is just equal to 1, right? So that means that this would be the greatest power. This would be like the greatest value for the power of 11. So that means that starting from 11, so 11, 13, 17, all those would just be, all those numbers would just not be part of the prime factorization of n. And this is just doing it the long way, right? So you could have, you would have also done d of 5 to the power of 1, and then so on and so forth. And if you multiplied all those numbers together and you added the digits, it would still be equal to 9. But this is just a shortcut that you could have found because you know that the prime factor definitely is 9. One of the prime factors is definitely 3 squared. Okay, now moving on to or are there any questions? Okay, so this one is going to be slightly longer. Okay, you know what? I'm gonna go back over here. Let's review this part. Okay, so for this math contest question, you're gonna have to be using this one. So if, so remember that this is in the form f of x is equal to b to the power of x, right? So if b is somewhere in between 0 and 1, then this is what the graph looks like, right? So basically, the smaller the number, or the smaller the x is, so the smaller the exponent is, the greater the y value, right? So the greater the product. So you're gonna have to be using this graph basically to figure out this following math question. Okay, so over here. Okay, once again, this is blurry. So I'm going to rewrite this. So this is a, you know what, I'm gonna rewrite it here. So a of k, right, in curly brackets, where k is equal to 1 all the way until 2011. So basically what this notation means is given you have a of k, for the values of k where k is equal to 1 all the way until 2011 inclusive. So let this be the sequence of real numbers defined by a of 1 is equal to 0.201, a of 2 is equal to 0.2011 to the power of a1, and then a3 is equal to 0.20101 to the power of a2. Okay, and then a4 is equal to 0.201011 to the power of a3. And in general, this you don't really have to care about. Okay, this part you don't really have to care about. This is basically just the pattern of the decimals given whether k is odd or even, and then rearranging the numbers in the sequence. So this sequence here in decreasing order produces a new sequence for, let me rewrite that. So b of k, same thing where k is equal to 1 all the way until 2011 inclusive. What is the sum of all integers k where 1 is smaller than or equal to k, which is smaller than or equal to 2011. So basically all numbers from 1 to 2011 inclusive, such that a of k is equal to b of k. Okay, so basically what this question is asking for is for a of k, so the same term numbers, right? K has to be equal to k. Okay, so the term number of a must equal to b of the same term number. Okay, so basically this would be, let's just say a of 1, right? A of 1 is equal to 0.201, right? Let's just say b of 1 is also equal to 0.201. Okay, just so you know, it's not. Then in this case, 1 would be the answer. Okay, if let's just say a of 111 is equal to some number, let's just say 1, and then b of 111 is equal to 1, then the answer would also be, then if both of these two were true, then the answer would be 111 plus 1, which is equal to 112. So that's basically what they're asking for. So this k value here has to be the same. And just to give you guys a hint as to how to do the question, so you're going to be using this graph over here. This graph is f of x is equal to 0.2 to the power of x. Okay, and the reason why we use 0.2 as the base instead of 0.201 is because using 0.201 is unnecessary, right? All these numbers, right? All these numbers are really close to 0.2. And so this is like 0.2 is basically the term that you can use to visualize the values of all these exponents, right? I should also put one here. Okay, so using this graph, right? Using this graph, you can basically estimate the value of a of 1, a of 2, a of 3, and a of 4, right? So this question, right? This question is basically trying to confuse you by adding multiple decimals, but really you just have to focus on the 0.2s of each decimal, and then you'll be able to solve this question. Okay, let me scroll back to the question. I'm gonna zoom out a little. Okay, and also to solve this question, I have to find a pattern of some sort. in order to find like the sequence of A of one, right? In order to find what is the pattern of A of one, so you can find it in decreasing order. This question is could take a long time, so I'll give you guys 3 minutes, or you know what? I'll give you guys 4 minutes to do this. The time is up. So, as I said earlier, we will be using this graph to do the question. So we will be comparing each of these terms, right? We'll just be comparing the first four terms in order to find a pattern. So comparing A of 1 and A of 2. So we have A1 is equal to 0.201 to the power of 1. So we can I'm just going to be saying 0.2 from now on. Okay, no need for the rest of the decimals. And then A2 is going to be equal to 0.2 to the power of A1. And remember, A1 is equal to 0.201. And so 0.1, where is that? That's going to be here, right? Because 1 is the x coordinate. This is the x value here. This is 1, and then 0, and then this is the y-intercept here. And so A of 1 is here. That's its point on the graph. And A of 2 is 0.2 to the power of 0.2. And where is that? That's going to be approximately somewhere over here. And as you can see, this is obviously much greater than A1. And so therefore A1 is greater than A2. Okay, and now comparing A2 and A3. Okay, so we have A2 is equal to 0.2 to the power of A1, and A3 is equal to 0.2 to the power of A2. Okay, A2 is here. And so this value here is somewhere close to 1, right? And so because it is somewhere close to 1, right, we can assume that A3, right, we can estimate A3 is somewhere here, right? So that means that A2 is greater than A3. Okay, well now we know that A2 is greater than both A1 and A3, but we don't know the order of A1 and A2 and A3, like which one is smaller, which one's bigger. So now we have to compare A1 and A3. Right, forgot. I should not have put that. Okay. And now we have A1 is equal to 0.201 to the power of 1. And then A3 is equal to 0.2 to the power of A2. Now, as you can see here, A2 is not at 1 yet, right? It is at 0.2. It is somewhere, it's the x-axis. So this is pretty much 0.2 here, right? And this is obviously greater than 0. And so we know that A2 must be smaller than 1. And because of that, that means that A1 must be smaller than A3. And so that's why I put A3 point somewhere here earlier. And so now we have this. And now we can compare A3 and A4. Okay, and A3 is equal to 0.2 to the power of A2, and A4 is equal to 0.2 to the power of A3. Now A3 is here, right? A3 we estimate is around here. And A4, right? A4 is 0.2 to the power of A3. And because A3's value is somewhere close, or like it's a low number, right? It's a small number. And so that means that A4 is going to be somewhere here. And we know that A4 must be smaller than A1, or sorry, not smaller than A1, smaller than A2, because A2, A2 is greater than A3, right? A2 is greater than A3, meaning that A2 must be a larger number than a4 because a4 a is to the power of a3, right? a4 is equal to 0.2 to the power of a3. This is to the power of 2. And so we know that this must be a pattern. And so therefore, in the end, we have a1 is smaller than a3, is smaller than a4, is smaller than a2. And there is a pattern here, right? Is the first the odd numbers in increasing order, all the way until the largest even number, and then decreasing odd even numbers from there. So the pattern must be a1 is smaller than a3, all the way until a 2011, which is smaller than a of 2010, and then from there decreasing all the way until a4, which is smaller than a2. Okay, so that means that in decreasing order for the a, so like the a values, the a of k values in decreasing order will be starting from a2 all the way until a1, right? a2 to a4 all the way until a1. And so the sequence for b is, or sorry, yeah, so the sequence of b is b1 from here and then going this way. Okay, now you'll see why I wrote it in this, in like this order in a second. So now we must find the correlation between between the terms of a and b, right? We have to find the correlation between the term number, right? And from b1 to b 2000, or sorry, 1015, I believe. Yes, yeah. And so like for these terms, they will never equal to the term for a. Reason being is, as you can see here, when when the term number is 1 for b, a is 2. When b is 2, a is 4. Right? So all the term numbers for a will be twice the term number for b. Okay, so from basically here, all these term numbers, they will not work. So that means that the term number must be somewhere here, right? From A1 to A 2011 and B 2011 to B 1016. Okay, so now we must, or sorry, B 2006, 1006, sorry. So we take the pairs, okay? So we basically pair up the correlating terms, right? So A1 is equal to B 2011, A3 is equal to B 2010. And so that is what we write over here. And we number them as 1, 2, and then so on and so forth. So this one will be 1, this is 2, all the way until this one. I believe this is just 1005. Right, yeah. And then we let x represent the pair number. Sorry about the alarm. We let x represent the pair number. So the term number, once you like fiddle around with it, right, you get b is 2012 minus x, and a is 2x minus 1. Okay, that's basically the pattern of the term numbers. And so now that we have the pattern, right, now that we have the pattern, we can now solve for x. Right now we can solve for x. So we have 2012 minus x must equal to 2x minus 1. We bring this x over here. So now that becomes 3x is equal to, we also move this one over here. add it to 2012. So we have 3x is equal to 2013. And so x is equal to 671. Okay, so now we just sub in this value into one of these two equations. I just chose 2x minus 1. You can also use 2012. You'll get the same answer. So that's 2 times 671 minus 1, which is equal to 1,341. And so the answer is C. And yeah, this is the last math contest question I'll be going through. Are there any questions? Well, then I will stop sharing.